Here in this second part, we'll jump ahead a little bit, and we'll look at the Jacobian. The Jacobian is a determinant. Remember, we've used determinants before. We've used them to find cross products. We've used them to find Hessian matrices. Now we're going to look at determinants to help us to solve these problems that involve a substitution. The Jacobian, at the end of the day, is kind of like your du in the u substitution. So the transformation g and h, your differentiable functions on a uv plane. The Jacobian in terms of u and v. So whatever you come up with here is going to have u's and v's in it, no more x's and y's. It's going to be the partial derivative of x with respect to u, partial derivative of x with respect to v, and then the second row will be y with respect to u, y with respect to v. There are 3x3s of this as well, and we'll get to that towards the end. Then how do you find the determinant? You multiply across. So go this way, and then subtract the other direction. So partial x with respect to u, partial y with respect to v, minus the 2 along the diagonal in the other direction. So we'll practice a couple of Jacobians first, and then we'll figure out what the Jacobian is used for. So here's my first example. Find the Jacobian for x equals 4v, y equals negative 2u. Right, so for number 1, when I set up my determinant, I'm going to do the partial derivative of x with respect to u. What's the partial derivative of x with respect to u? Well, if x is 4v, if I derive with respect to u, I just get 0. Right, what's the partial x with respect to v? It's 4. So that's my first row across. Second row will be the y's. So partial y with respect to u is just that coefficient there, that negative 2. Partial y with respect to v is 0. So when I calculate it, I get 0 times 0 minus 4 times negative 2. My Jacobian is 8. Done. All right, look at the second one. Second one says x is equal to u over v, and y is equal to v. So I can write my x this way. I can write it as 1 over v times u. So that when I go to set this up, the partial derivative of x with respect to u is just this quote-unquote constant that's in front of it, right? If I'm deriving with respect to u, that v is just treated as a constant, so I get 1 over v. So sometimes my Jacobian will have variables in it. All right, we did the partial x with respect to u. How about the partial x with respect to v? Now let's write this as uv to the negative first. So when I derive it with respect to v, I'll get negative uv to the negative second. So I'll get negative u over v squared. All right, the second row should be easier. Derivative of y with respect to u is just 0. There's no u in there at all. And there's 1v. All right, cross multiply this guy. 1 over v times 1 is 1 over v minus 0. Oh, just 1 over v. Okay. This third one's going to be a little bit more challenging, because you notice in the first two problems, I already gave you x in terms of u and v. Not in this case. In this case, I gave you u in terms of x and y, and v in terms of x and y. First thing I have to do is I've got to solve for x and y. So let's bring this up here so we get a little space. Maybe I can eliminate the y's. So if you thought of this as one of those old-fashioned linear combinations, where you have an x plus 4y equals u, and you've got a 3x plus 2y equals v, what would get rid of that y? How about multiplying the bottom row by negative 2? So you got x plus 4y equals u, and you got negative 6x minus 4y equals negative 2v. Okay, add those together. Negative 6x plus 1x is negative 5x. The y's go away, and what do you get on the other side? U minus 2v. So the first thing here is eliminate the y's. Right, if you want to solve that thing for x, divide both sides by negative 5, and you get x equals 2v minus u over 5. I'm actually going to switch this back around. I'm going to make it negative 1/5 u plus 2/5 v, because it'll make things a whole lot easier if I can put my u's and v's in the right order so I don't get confused at the end. I mean, I do get confused, so let's not confuse me anymore. All right, that next step is let's eliminate the x's. So let's start with those same lines. X plus 4y equals u, and 3x plus 2y equals v. This time, let's hit the top row with a -3. So I get -3x minus 12y equals -3u, and 3x plus 2y equals v. I get rid of my x's, and I'm left with -10y equals -3u plus v. Divide through by -10, and what do I get? Y equals 3/10 u plus, or actually minus 1/10 v. Okay, you realize that by writing it this way, I basically have the Jacobian already set up for me. The partial derivative of x with respect to u is -1/5. Partial x with respect to v is 2/5. Partial y with respect to u is 3/10. Partial y with respect to v, -1/10. So I end up with positive 1/50 minus 6/50, which is -5/50, which is -1/10. Can the Jacobian be negative? Yes, absolutely the Jacobian can be negative. When we evaluate it, we're going to end up evaluating the absolute value of the Jacobian, so even if it's negative, it will become positive when it goes into our calculations. All right, so what do we use the Jacobian for? Let's take a look. This is the formula for change of variables in double integrals. So I've got some region. It's some funky, weird region that I don't want to deal with. So I'm going to want to convert it. So I've got this f of xy integrated over some area. I'm going to change this to integrate it over a different area. I'm going to call that region S instead of R. I'm going to evaluate them in terms of u and v, right? G of u, v, h of u, v, times the absolute value of the Jacobian integrated over the area. So how does this work? Let's take a look at this problem. I put all the directions over here, so in case you're working on trying to do a homework problem or something like that, you can follow along the steps. So this region over here is bounded on the x's from 0 to 2, on the y's from y equals x to y equals x plus 4, and I'm integrating an x squared y, and I'm told what variable substitutions to use. Let's let x equal 2u, and let's let y equal 4v plus 2u. So the first thing it says, substitute into R to get a new region with boundaries in terms of u and v. Because right now, the boundaries are in terms of x and y. I would like boundaries in terms of u and v. All right, so let's come over to the top here and get some work done. So step 1, I need boundaries in terms of u and v. So I was told the x's went from 0 to 2, and the y's went from x to x plus 4. Well, the problem said to use x equals 2u, so I'll replace that x in here with a 2u. And so the u values go from 0 to 1. How about over here? Well, again, we got to replace that x with a 2u. Now we get to replace that y with a 4v plus 2u, again, because the problem said to. And on the other side, the x plus 4, again, let's replace that x with a 2u. All right, what can I get rid of? I can get rid of a 2u from everything, right? I can subtract the 2u here, subtract the 2u there, subtract the 2u there, and I get 0 is less than or equal to 4v is less than or equal to 4. Divide through by 4. And look at that. Instead of having to deal with those x's and x plus 4s and everything else, I'm back to my unit square. It will not always turn out this way, but in this case it did. All right, second step is calculate the Jacobian. So I was given x equals 2u and y equals 4v plus 2u. So my Jacobian is going to be the four partial derivatives. So the partial x with respect to u is just 2. Partial x with respect to v is 0, right? There's no v in that first line. In the second line, just watch because the order that I have it written up there is not the same as the Jacobian. So the partial y with respect to u is 2. Partial y with respect to v is 4. Right, 2 times 4 is 8 minus 0. Jacobian is 8. Now the third step is to go back to my original function and get it in terms of u and v, right? It says replace x, y in the integrand with functions of u and v. So my third step will be to take that double integral of x squared y over some area and replace the x with a 2u and replace the y with the 4v plus 2u. All right, so that gives me a 4u squared times 4v plus 2u, and now distribute. I get a 16u squared v plus 8 u squared times u is u to the third. Okay. Set up the double integral. I'm going to get the double integral of what I have up there, 16u squared v plus 8u to the third. And then I need order of integration. Well, in this case, it doesn't matter because they're both 0 to 1. So dvdu, let's say, from 0 to 1, from 0 to 1. Now, here's what you don't want to forget. The Jacobian. The Jacobian was 8. So we're now going to multiply this by 8. All right, from here, it would probably help us if we pulled out an 8 twice. So I'm going to pull out this 8 here, that's the Jacobian. And then you notice those are both constants of 8 also. So let's take that line and move it up here. So my next step will be simplify and evaluate. And I'm going to pull a 64 on the outside. 0 to 1. 0 to 1. 16 divided by 8 is 2. So I get 2u squared v plus 1 u to the third dv du. Now, if we set this up right and we have a nice problem, this part should be easy because we've set it up with nice limits of integration. So don't forget what you're evaluating. The first time you're evaluating with respect to v. So when I take the antiderivative of that first term with respect to v, I get 2u squared v squared over 2 plus u to the third v. Right? Those go away. And I'm evaluating it where? At v equals 1 and v equals 0. Well, v equals 0 is going to yield nothing. V equals 1 will give me u squared plus u to the third. All right, now I'm going to evaluate that from 0, or integrate that from 0 to 1, and I'll multiply it by 64, integrate with respect to u. So I get 64 u to the third over 3 plus u to the fourth over 4. Right, clearly, if I put a 0 in, I yield nothing, so this will give me a 64 times a third plus a fourth. I'm going to have to go down to 12ths, which is not bad, right? 1/3 is the same thing as 4/12. 1/4 is the same thing as 3/12. So I'll end up with 64 times 7 over 12. Can I simplify that a little bit? I could take a 4 at the top and bottom. That'll give me a 16 to 3. And so 16 times 7, 112. So I ended with 112 over 3. That's the value of that double integral. All right, so I'm going to zoom out because I've actually been working my way across my screen just to show you what it is that I did. All right, so the first thing is, let's ignore the part up on top there. First thing is we took our function, we set boundaries in terms of u and v. So I took my x's and my y's and I converted them to u's and v's. I calculated the Jacobian. Then I replaced the x's and y's in the integrand with something that was in terms of u's and v's. Set up the double integral with the limits of integration and the variables, the du's and the dv's. And don't forget to multiply it by the Jacobian. And then the last step was just simplifying and evaluating. All right, let's try one more and then we'll do one more video with the triples. In this case, let's take a look at the boundaries first. It says we're evaluating the double integral, square root of y squared minus x squared. R is the diamond bounded by those four lines. Y minus x is 0, y minus x is 2, y plus x is 0, y plus x is 2. Did they give us a substitution for this one? It doesn't look it. So we're going to have to come up with our own substitution. This region, when I graph it, y minus x is just y equals x. That's this line over here. The second one is going to be y equals x plus 2, which is that line over there. The second two will basically be y equals negative x. Y equals negative x comes down like this. And this will be y equals negative x plus 2, which comes down like that. So it's this diamond region in the middle that we're trying to integrate over. Well, it would be nice if I could do something to kind of turn it around so that I had constants as limits of integration. But what am I going to use for my u's and my v's? It's perplexing until you look a little bit closely and realize, look at this. This is a y minus x, and that's a y minus x. On the other side over here is a y plus x and a y plus x. And on the other side, they're both equal to constants. So what if I just let u be y minus x on the interval from 0 to 2, and I let v be y plus x, again, on the interval from 0 to 2. But now, what I'd like is I'd like those things in terms of x's and y's. I need to solve for x and solve for y because I need it for the Jacobian. So great, now I have a substitution. How do I solve that for the Jacobian? All right, let's come over on the side and rewrite these so that I can figure out what to use. So the two equations we came up with were u equals y minus x and v equals y plus x. Add them together first. So if u is equal to y minus x and v is equal to y plus x, if I add those two things together, I get rid of my x. So I get u plus v is equal to 2y. Switch it around, divide by 2, I get y equals half a u plus half a v. All right, we added them to get rid of the x. Let's subtract them to get rid of the y. So I get u equals y minus x, and negative v equals negative y minus x. So I just hit that second row with a negative 1 because I want to get rid of my y's. So I end up with u minus v equals negative 2x. Divide through by negative 2, and I get x equals negative 1/2 u plus 1/2 v. All right, so now let's set up the Jacobian. The Jacobian is going to be all the partial derivatives. So the partial x with respect to u is going to be negative half. Partial x with respect to v is a half. For the y's, the partial y with respect to u is a half. Partial with respect to v is a half. So if I set it up like that and put all my u's and v's in the right order, then the Jacobian becomes real easy to set up. Evaluate negative half times a half is negative quarter, minus half times a half is a quarter. So this gives me negative 2/4, which is negative 1/2. You notice in the formula, it says the absolute value of the Jacobian in terms of u and v. So that'll give me the absolute value of negative 1/2, which is 1/2. So hang on to that number. We're going to need it. That's the Jacobian. All right, now let's go back to our original formula. Our original formula was the square root of y squared minus x squared. So I need a double integral square root of y squared minus x squared over some area. So let's work on the integrand. What did we come up with for y's and x's? We said that u was y minus x and that v was y plus x, and then we solved them. So when we solved them, the y came out to be a 1/2 u plus v, and the x came out to be a 1/2 v minus u. And then we've got to square them, right? So that's my y squared minus x squared. Let's expand this and simplify it. Half squared is a quarter, so I get a quarter. Now, when you expand to u plus v, you're going to end up with a u squared plus 2uv plus v squared, all right, minus, again, a quarter. Now you're going to get a v squared minus 2uv plus u squared. Can you see that if I got a quarter u squared over here and a minus quarter u squared over there, they're actually going to go away? Same thing with the v squares. I got a quarter v squared over here and a minus quarter v squared over there, so they're going to go away. A quarter times 2uv is a 1/2 uv minus a minus. Again, a quarter times 2 is a 1/2. I just get uv. uv where? Under the radical. So now, let's set it up. Double integrals are both going to go from 0 to 2, because in our original problem, that's what they did. They went from 0 to 2. So I get integral from 0 to 2, integral from 0 to 2. The square root of uv is going to be the square root of u square root of v. And where was our Jacobian? Our Jacobian was the 1/2. So we can pull the 1/2 on the outside over there. What order are we going to do the limits of the integration in? Really doesn't matter in this case. I don't know. Let's do dvdu. Here's the trick. First time I'm integrating with respect to v, meaning that the u is just a constant. So I do it that first time around. I keep the square root of u. When I integrate v to the 1/2, I add 1, divide by the new power. Well, dividing by 3/2 is the same thing as multiplying by 2/3. I'm going to evaluate this for v equals 2 and v equals 0. So this will give me 2/3 square root of u times 2 to the 3/2 power. If I put a 0 in for v, goes away. All right, the second step now is to integrate with respect to u. Why not take this 2/3 and this 2 to the 3/2 and just pull it outside? So I've already got a 1/2 over here. I now have a 2/3, and I have a 2 to the 3/2. So let's pull all that out. Integrate from 0 to 2 of the square root of u du. So again, I'm going to get a u to the 3/2 times 2/3, evaluated at 2 and at 0. So this will give me 2/3 2 to the 3/2. All right, we're getting somewhere. Let's take all this and put it together. What do I have? I have a 1/2. I have a 2/3. I have a 2 to the 3/2 power. And then from this, I have another 2/3. And I have another 2 to the 3/2 power. Yeah, these will go away. And so I'll get a 2 over 9. Here I've got two powers that have the same base add exponents. So 3/2 plus 3/2 is 6/2, which is 3. All right, keep going. 2 to the third is 8, so I get 2 times 8 over 9, 16 over 9. And there's my answer. So in this case, it was a little bit more challenging because we had to come up with our own substitutions. In the previous problem, we were given the substitutions. This time, we had to come up with the substitutions. And then once we had the substitutions, then we had to go back and rewrite them so that they were x in terms of u and v, y in terms of u and v. Once we've got that done, then the Jacobian, substitute, limits of integration, and then just plug through the evaluations. All right, we'll do one more video with what happens when you have 3 variables.